Hello everyone, I'm Shreyas and this is my partner Jofin. Welcome to the demonstration of our project DMAAccelerated Real-Time Signal Acquisition and Visualization. In simpler terms, we built a high-speed 6-channel digital oscilloscope from scratch using an STM32 microcontroller and Python. So normally if you ask a microcontroller to read 6 analog sensors and send that data to a computer, the CPU gets completely overwhelmed. It gets trapped in a cycle of waiting for the ADC, reading the data, and waiting for the serial port. To solve this, we bypass the CPU entirely for data collection. We designed a hardware level pipeline that reads, packs, and streams data automatically. So this is our system architecture. As you can see, there's an analog signal that is being given to our ADC. The conversion happens here. After the conversion is done, our DMA engine picks it up and stores it in our memory. And after the memory buffer is full up to some extent, then the CPU comes into picture and sends it to a Python GUI via UART. So as you can see, the analog signal, our input limitation is 0 to 3.3 volts. Beyond this voltage limits, we could fry the pins of a microcontroller. So all incoming signals must be offset and scaled within that 3.3 window. So now here comes our ADC. We configured both the ADCs, ADC 1 and 2 in regular simultaneous mode. This means ADC 1 and 2 share a single hardware trigger. At the exact same microsecond, ADC 1 samples channel 1, while ADC 2 samples channel 4. The STM32 hardware then takes those two 16-bit readings, packs them side by side into a single 32-bit register, and fires a signal to our secret weapon, the DMA. So the DMA stands for direct memory access. When the ADC is finished reading, they don't bother the CPU. The DMA controller acts as a background worker, scooping up the 32-bit packed data and dropping it straight into our RAM over here. So we're using a ping pong buffer strategy. The DMA is set to circular mode with half complete and full complete interrupts. While the DMA is filling the first half of our memory array, the CPU is safely packing and transmitting the second half. They never step on each other's toes, allowing for 100% continuous gapless data acquisition. So now, after the DMA has completed its work, now our CPU is capable of sending the data to our Python script via UART. But if Python just guessed where to read this massive stream of raw bytes, the graph would be corrupted instantly. To fix this, we designed a custom protocol. Every 14-byte packet starts with 2 sync bytes. These are the 2 sync bytes over here, followed by 12 other bytes, which have the information of all the 6 channels. So once Python extracts the frame, it reconstructs the 12-bit integers, converts them back to real-world voltages, and pushes them into a matplotlib animation. Okay, so to sum it up, here's our function generator, which is giving input to one of our ADC input channels over here. Once the ADC starts converting, once the ADC completes converting, the DMA picks it up and stores it in a memory buffer, and then the CPU takes it and then sends it to our PC via UART like this. Now this is the input that we are sending to our microcontroller. It's a square wave with frequency 330 Hz and amplitude of 1 volt peak to peak. Now this is what we are seeing on our Python GUI. We've included many features like we could enable different channels at different points. Like we could enable or disable any channel. Like the channel 6 is what we are seeing right now. I've disabled it, but I've enabled it at the same time. There are different other features like pause. We can scale it up as well, scale it down. So that's it. As the baud rate for our UART transmission is 921600, the time per frame we have is 152 microseconds, which gives us 6582 maximum frames per second, due to which the maximum frequency limit we have is around 650 Hz. Like if we get to beyond this frequency, we may not be able to get the exact signal that we are giving as input. So for example, now there's a sine wave of 500 Hz. On our oscilloscope, we could see a very good sine wave, which is exactly what we are giving. But now as I increase the frequency to let's go beyond 650 Hz, we could see that part of the wave is being clipped. Like it's no longer a perfect sine wave. So that is the frequency limit that I was talking about. So beyond some 650 Hz, we may not be able to get the exact input signal that we are giving. So that this is our project, and thank you.